In this video, we'll go through a step-by-step process for sizing control valves for compressible fluid using the ISA and IEC's recommended procedure. For this example, we'll assume superheated steam is to be supplied to a process designed to operate at 250 psig or 17.2 bar. The supply source is a header maintained at 500 psig or 34.5 bar and 500 degrees Fahrenheit or 260 degrees Celsius. An NPS 6 or DN150 standard schedule line from the steam main to the process is being planned. Note that a 6-inch standard schedule pipe has an inside diameter of 6.1 inches. Also, make the assumption that if the required valve size is less than NPS 6 or DN150, it will be installed using concentric reducers. Now let's go through the process to determine the appropriate Fisher ED valve with a linear cage. The first step is to specify the variables required to size the valve. The desired valve design is a Class 300 globe valve with an assumed size of 4 inches and a linear cage. The other service conditions are shown. We'll keep these conditions on screen throughout for reference. Start by trying an NPS 4 or DN100 Fisher ED valve with linear trim at 100% travel, where CV equals 236 and X sub T equals 0.69. For step 2, determine the equation constants N sub 2, N sub 5, and N sub 6, N sub 8 or N sub 9. From the equation constants table in the control valve handbook, we can see that N sub 2 equals 890 and N sub 5 equals 1000. When mass flow rate is given in pounds per hour and density is given in pound mass per cubic foot, use N sub 6, which equals 63.3. In step 3, determine the piping geometry factor, or F sub P, and the pressure drop ratio factor, or X sub TP, adjusted for the attached fittings. First, find the necessary resistance coefficients needed when the upstream and downstream pipe sizes are the same. Use the standard K sub 1 equation. Plug in your variables for a result of 0.16. Now use the standard K sub B1 equation and insert your variables for a result of 0.82. And use the standard sigma K equation and apply the variables for a result of 0.49. Now let's calculate the piping geometry factor, or F sub P. Use the standard F sub P equation, plug in your variables for a resulting F sub P value of 0.945. For the last part of step 3, calculate the pressure drop ratio factor, or X sub TP. Use the standard X sub TP equation and insert the variables for a calculation of 0.67. Step 4. Determine the pressure drop ratio to use for sizing, or X sub sizing, and the expansion factor Y. Start by calculating the ratio of specific heat's factor, F sub gamma. Use the standard F sub gamma equation, apply the gamma value of 1.33 for a value of 0.95. Use this result to find the choked pressure drop ratio. Use the standard equation, plug in the variables for a result of 0.64. The choked flow pressure drop ratio is greater than the actual pressure drop ratio, so X sub sizing equals X, which equals 0.49. Then plug in the variables to find the expansion factor, Y, for a result of 0.75. Finally, for step 5, calculate the required flow coefficient, or CV. Use the standard equation for CV and apply the variables for a value of 173. Repeat the calculation using the published X sub T values for the valve until agreement is obtained between CV and X sub T. This results in a required CV of 169 and X sub T value of 0.754. This occurs at about 66% open, so the NPS 4 DN100 Fisher ED valve with linear trim would be an acceptable solution with respect to capacity. The next smaller size of ED valve with linear trim has a rated CV of only 148, so it would not be an appropriate valve for this situation. So that's the process for sizing a valve for compressible fluid. Visit Fisher.com or contact your local Emerson sales office for more information.